Chapter 13, Circular Motion. You are all masters of deriving the expressions for the velocity and acceleration in polar coordinates. Now we can begin to reap the benefits of this derivation. This chapter has two parts. The first part is devoted to using Newton's second law with the IR and I theta components of the force and acceleration to solve all kinds of problems that would otherwise be unsolvable. We will then express the forces in terms of their IR and I theta components and set F sub r equal ma sub r and F sub theta equal ma sub theta. You need to remember that the definition of IR is along R pointing out. That means a force pointing in towards the origin has a negative IR component. That minus sign is probably the most missed sign in all of first-year physics. Now we use the results of the last chapter, namely a sub r, second derivative of r minus r omega squared, and a sub theta, 2 dr dt omega plus r alpha. There are certainly situations where these equations are mathematically pretty nasty, but even then, we can learn a lot from them. There are also many much simpler situations, such as motion in a circle, where the derivatives of r are zero and the equations are easy to solve. One example is shown in the video, where an open container of water is swung in a vertical circle. You could calculate the minimum speed you would have to give the container in order to stay dry. You could also predict at what angle the liquid would spill if you went too slow. There are all kinds of problems we can solve now that we know polar coordinates. One of the problems in the book has a block sliding on a frictionless track. And the question is, how high up on this straight part do you have to put the block so that it'll go around and just make it around the circle? This could be a model of a roller coaster. This could be a model of a skateboarder who was defying death by going on such a track. And it's relatively simple for us. It's a problem in the book to calculate how high this has to go. As long as it's high enough, it goes right around the circle without falling off. If it's too low, it falls off the track. Exactly the same principle will hold if we fill a bucket with water and swing it in a vertical circle. As long as we give it enough velocity, the water will all stay in the bucket. You might try this at home. Swing it fast enough, the water all stays in the bucket. If you don't swing it quite fast enough, the second part of this chapter deals with the special case of a wheel or disc rolling without slipping. In that case, there is a relation between the linear motion of the wheel and the rotational motion about the center of the wheel. There are many problems that can't be solved without using this relation. The same type of relation holds when a rope goes over a pulley and there is so much friction that the rope does not slip. In that case, the relation is between the rotation of the pulley and the linear motion of a weight hanging from the rope. Summary. The expressions for the components of the acceleration in polar coordinates derived in the previous chapter are combined with Newton's second law. This leads to equations that describe all kinds of motions, including the simple case of an object going in a circle. It is also shown that in the special case of rolling without slipping, the rotational properties of a wheel are related to the linear motion of the wheel's center. Gig 'em.